I'd like to welcome everyone to our, I presume will be the last seminar of this semester. And we're introducing Dr. Cliff Spiegelman, who's a distinguished professor. Got that right? Is that correct? Distinguished professor of statistics. Yes, I remember. Now, at the even more distinguished Department of Statistics at Texas A&M University. And he's going to be favoring us with a talk on some of the recent developments in the computationally intensive methods of estimating errors, namely the Gap Bootstrap, which I don't think you got at the Gap, did you? anyway, okay.
You'll find the gaps in the logic. Thank you, Ron. Pleasure to be here. So thank you. And I can probably put my hand over this if it's too loud. So this is joint work with some transportation engineers. Justice is a student just graduated from University of Nebraska, and Larry Orlett is the chair, distinguished professor of transportation at University of Nebraska Center. And Shuman Lahiri is a very famous guy in bootstrapping who joined the A&M Stat Department from Iowa State a few years ago. And I think my name's first only because I'm giving the talk. All right, so I thought I'd start out with a slide about uncertainties. And everybody's taken a stat course and you know how to put on uncertainties. And you follow all the rules, and this is like neutron lifetime. At different years, this is the neutron lifetime value, say at 1963, 4, 5, and so on. And there's lifetimes of mu mesons and various fundamental constants, and they're really physically constant. And the one thing you should see from this slide is, despite the best efforts of all the stat courses, the stuff sucks. And so you can see people put uncertainties, rather wide uncertainties here, but they were missing a factor. Then they got the factor, and then they thought they're missing another factor, and so on. And that would be true with all of these. So, and these are fundamental constants with rather usually high-level physicists and chemists and the like putting the uncertainties on. And so, just because there's a nice algorithm and there's a theory that says something should be the uncertainty doesn't mean it was gotten right. And that's the caveat, because it's real simple. The stuff we're going to talk about is much more complex, much less pulled out of the woods. And
what's the third one there? The third one down on the
this one. This one?
Yeah, that's really weird.
Yep. And I don't know why that happened, but it did. Yeah. And these are the actual co-data. These are the official international values for these parameters. All right, so, and the point is that these problems are very much pulled out of the woods. There's no problem defining what neutron lifetime is. We're not talking about pollution at a particular day, at a particular minute, at a site, and how general it is, or where it came from. We're not talking about what the traffic is in a particular location. When we say the average speed is, do we mean time mean speed or distance mean speed, or different ways to measure speed? These are very defined problems.
For a long time, they were thought that, boy, we really know that's certainly not below this one value. Then they go, oops.
That's it. Right. Okay, so this is the really highly defined case. So now we're going to get on, and nobody should think that we're doing better when we do more complex stuff, but we'll go do more complex stuff. So I guess page down should.
Sometimes your first idea is best.
Function page down. I don't know how to move the page down. Oh,
where's the fellow?
Let's try. Okay, I can hit. I can do the.
There you go.
Okay. All right. So the focus today, or what we're going to provide a partial solution for, is multivariate data analysis, either receptor modeling or OD estimation and transportation, which is origin destination estimation. It's useful for planning shopping malls or other things, traffic routing, to know what percentage of the traffic gets on and off at various on-ramps. With Ron Henry here, I guess I should explain for you if you don't know what receptor modeling is. It's sort of unmixing environmental pollution to figure out the sources and the amount, the contributions from various sources, and the profiles for those sources, sort of the cake mix formula. All right, so traffic speed and volume are high dimensional. It's not uncommon to have thousands of entrances and exits around a city. Air pollution monitoring data, high number of species, hourly data, thousands of observations. Same thing with health data, morbidity and mortality data. We're going to assume that, and it's an assumption, and all models are wrong, sometimes they're useful. Time dependence has a finite range. Autocorrelation is near zero after a fixed range. So variation in particulate air pollution today is typically not dependent on particulates from a week before or after, or you can make it a month before or after. You can pick the time lag. Variations in traffic speed and volume today usually don't depend on yesterday or tomorrow. Unless there's an accident that doesn't get cleared, you start again. And this is errors off the mean model. I mean, the pattern for the mean can repeat from day to day, but the variations from the pattern typically don't, and variations of deaths today are not usually dependent on those from a week before or after, unless there's an unusual event. So this is very general. Receptor modeling, pioneers are Ron Henry and Phil Hopke. They decompose pollution measurements into source profiles and contributions. It's part of environmental forensics. You can check on self-reported emission inventories, find health effects for pollution source types. This is vanilla receptor modeling. Just write down some equations where the Y is the measured ith pollute, Yi is the ith measurement from the receptor, Q the number of sources, P is the profile, the percentages, if you will, of each pollution type. The alpha IK are the amounts or contributions, and the E's are the errors. Epsilons are the errors. In matrix form, it looks like that, and the same equation, just in matrix form. OD modeling, origin destination modeling, is a matrix required by many traffic applications. It's also used in microsimulation. So a microsimulation is, an example is TransSims, where, say, for a big city like LA, you would model every trip by every person in the city. So you would trips to the doctor, trips to work, trips out to lunch, trips to retirement dinners, you name it. They do that. Yeah, they don't put in the retirement dinners, but trips to lunch they do. They've done it for cities as large as Phoenix, in big cities. I don't know if they've done it for LA, but they've done it for big cities, Seattle. It's expensive to measure the ODs directly, so they estimate it. And here's some references. Least squares is often used, sometimes with what's called a gravity constraint, because there aren't enough observations to estimate anything.
What do you actually estimate?
Let's go what you ask. So here is say a route, and you know how many people get on here. You may get the origins, how many people get on, and you try to figure out, without measuring, where people get off. And you get counts along the highway, so here where these things are, but the counts aren't exact. Right. And so there's so people get on here and people get off, and you try to figure out and it's mathematically very similar to receptor modeling. It's quite similar. So let's see if I can go back. Previous. So these are least squares. Ron knows Byron Gajewski. He did his thesis in this area and applied it both to receptor modeling and OD estimation. And anyway, there's various, if you want more references, I can give them to you. And again, this is a typical application, very small scale application. This is a Mac PC issue, but up here are equations. Yeah, I'm going to do a dance.
Right.
Up here are equations, or should be up here if we
I would
put.
say flying bird.
Right, yeah, there we go. Where it looks very much like the receptor model, except it's OD estimation.
Yeah.
Okay.
You were worth $20 or $30 billion. You could make software this good, right?
Well, it's a Mac PC. It's the equation editor doesn't.
Yeah, I've had this problem too.
Okay, yeah. Okay, so now we have two complex models sort of as examples. Let's see how we can do it. So we can do propagation of error, which is essentially a Taylor series around the mean, and you drop the higher order terms and you hope that they're small and do the calculation. So it's change a nonlinear model to a linear model, or a linear approximation to a nonlinear model, and use the errors that you would get for the linear model, and supposedly everybody knows how to do that for linear model. Bootstrapping, that's resampling. You have a lot of data. You randomly take a sample of the size you have, calculate an estimate, put it all back together, take another sample, calculate an estimate. You keep doing it until you're tired, and then you calculate variances and standard errors from that. Now, block bootstrap, now the vanilla bootstrap sort of breaks if the data is dependent. You think you have more observations than you do, so you could just think of repeating.
With the serial correlation.
Yeah, serial, right. So the deal, if in the extreme case you have 100 numbers, but they're all the same number, and so you resample and you think you have samples of size 100, and you get a very low variance, but you should only. All right. So a way to correct that is block bootstrapping, where the data is taken in big blocks. So if you had 1,000 observations, you could have 50 blocks of size 20, contiguous blocks. And then resample, when you draw either a whole block or not at all. So you get 1,000. But then the problem is if you do it that way, the estimates that you get are not unbiased, and there's a very complicated correction, even for things like sample means. Nobody's ever worked it out for the kind of models we have here. And then I'll talk about something called the Gap Bootstrap, which is a simple idea. And I can give you the 2-minute elevator speech in probably less than 2 minutes of what it is. You take the data and break it into subsets so that the subsets themselves are independent. You use bootstrapping on the independent pieces, and then you use propagation of error to put the pieces back together. So all you do is you estimate the thing in pieces, simply take an average of the pieces you have, and then use, all you have to do is estimate the correlation between the pieces. And we'll do that under some assumptions. And it's quite simple. It's kind of like every smooth function can be approximated by, every function can be approximated by a piecewise straight line. And this is the same idea. You just take little pieces, do a good approximation on the pieces, and then put the pieces back together. All right. The Jackknife is sort of a leave one out rule. You take out an observation and see what you get. You can jackknife on the rows of these models or the columns. We'll discuss it a little better. The columns is actually simpler. There's fewer columns than rows, say in receptor modeling or OD estimation. You might have thousands or hundreds of thousands of rows. Columns usually, are tens of those numbers, or way less than the number of rows. And then there's Bayesian approaches. But these are columns are your unknowns and rows are your knowns? The columns are the O's or the D's, how many origins or destinations you have, and the rows are the number of 5-minute averages for speeds. If you're doing, if speeds are your thing.
Obviously, you have typically more observations than other.
In the transportation, not always, but in the transportation, in the environmental stuff, you typically have more rows than and the columns are number of distinct chemical species, or PM 2.5 species or something like that. So at least for the problems we're doing now, rows could be in the thousands, tens of thousands, or hundreds of thousands. Columns are in the high tens. Or, you could do the city of Los Angeles. I don't know the city of Los Angeles because I really don't know your traffic system. But in Houston, 3,000 or 4,000 entrances and exits would be the number. And sometimes you don't have, by the time you get done with bad sensors, you don't quite have as much data as you want. So typically n is bigger than p, but not always. All right, and this is not readable. It's just it's here for effect, which says that when you do these receptor models, you can actually write down. You can do propagation of error, and you can write down a formula. You don't want to look at it a long time. Okay, and this is from Unsug Park, a former student's PhD dissertation, and she worked out what it is, and again, it's only for
any point with the Kronecker delta should be avoided.
Right. That's it.
I'm not trying to Kronecker.
Kronecker. Yeah. No. Right. Kronecker cross product. Yeah. No. That's the point. All right. It's complex, and it depends very much on having the right model. It's very sensitive to the model. Now, you're always doing uncertainty, assuming the model is correct, but for example, you could estimate the mean of a normal observation, and you could assume it's normal. And if it's not normal, you're going to get something wrong. The error statements, the confidence interval is probably not going to be quite right, but the central limits theorem is going to save you, and it won't be totally off. If you are wrong on this calculation on the Taylor series, you really got it wrong. I mean, you're taking derivatives of the wrong stuff, so you're locked into something that isn't good. So you put your hand on your heart and say, I believe this model. All right. And also, the higher order terms in the Taylor series have to be truly ignorable. And I didn't give you the second derivatives on the previous slide, and you don't want to see them. It needs independent errors, and it typically needs large sample sizes because you need those second order terms to be small, and that typically happens when things average out. Okay. Bootstrap. It's very simple. Simple's good. It can be computationally intense for complex models. There are identifiability issues. When you resample, it's possible to resample the same observation many times. You typically do. Some get resampled lots of times. Some get resampled a few times. But particularly in these high-dimensional models, sometimes you need some particular rows in, and you might not get them. Case of dependent data, the estimated.
In the limit, it may not go to the true value.
Well, you got two limits going on. You
Right.
Sample size increasing and the number of bootstrap samples. But it's not bad if it was really independent.
Right.
In most cases, you're okay. But because of the identifiabilities, you could. I mean, if you lose the identifiabilities, there are the problems. In typical cases of dependent data, serial correlation, the estimated uncertainties are almost always underestimates because the serial correlation is positive. Block bootstrapping helps. Bias correction is needed. And we'll talk about gap bootstrapping in a little bit. Okay. Jackknife works for smooth estimates, doesn't work for medians or percentiles. It's an older method done by Quenneville first, and then Tukey and Quenneville, very famous in statistics. Many of you may have heard of the Jackknife. It works regardless of whether you have a closed form for the estimator or not. You don't have to do, it's not like propagation of error. It's true for the bootstrap as well. Yes, indeed.
I mean, that's the point of what you don't kind of
Yes. They're simple and they work well in many cases. Where they don't, where they sort of break is when the correlation. They're always done under the assumption of independent errors, and when you don't have independent errors, then you need a fix.
Yeah, our point, Mike, if you don't mind,
Sure.
In air pollution, the air pollution always follows a diurnal pattern. The ozone peaks in the noon and at the minimum in the night, and just day after day after day. And if you don't include that kind of serial correlation in your thing, your results are going to be highly biased. Okay.
So that's sort of the issue. And where bootstrapping does work for medians and percentiles, Jackknife doesn't. But The reason Jackknife is nice, it's not as computationally intensive, typically, and you couldn't do bootstrapping, like 30 years ago. I mean, there was no way to do it. I mean, computers weren't fast enough for something like this. I mean, when, I learned how to do receptor modeling in part working with Ron, but even when we did it for data now that would take like a fraction of a second to run these models, it was 8-9 hours. And, if you had to do that 1,000 times for a project, that wasn't working.
The computer doesn't get paid by the hour.
Right. That's it. Yeah, I know, but people want answers in real time. So here's a newer approach, and it was done by Park and myself. And last, I think it was published in 2007. You can do the bootstrapping on the columns for the models that we're doing. They're bilinear. It's sort of, if you take a look at the basic model and transpose the basic model, you still have a model that looks like the basic model. And the point there is, if you have, the Jackknife is sort of take each row out and compute a simulated residual for each observation. And if you have thousands of observations, that's thousands of these computations. Whereas if you have 10 columns or 30 columns, and you drop one column out at a time, you only have like 30 calculations instead of 2,000 calculations. And the other issue is it plays with the correlation structure in ways that I'm not going to go over here, but it's okay. So here's a basic model. There are some constraints. And instead of going down the rows, dropping one at a time, we're going to drop the columns out one at a time. Here is a bootstrap residual. You drop out the jth column. If you have p columns, you take p times the estimate with everything in minus p minus 1 times the estimate with the jth column dropped out. And that gives you the j pseudo value. And then essentially you compute the variance from those things. And there's a trick involved as to why this works in receptor modeling and will work generally with highly dependent data. When data is very correlated, like the columns are very correlated, it's called multicollinearity. You're doing regression, you have multicollinear predictors. If you drop one out, answers change dramatically. We want that because receptor modeling is an area where people understate uncertainties. Maybe not present company, but in general, I think, I know Ron tells the uncertainties are underestimated. By dropping a column out, it causes a whopping residual. And if you do this, you get these very big residuals. Not all of them, but all you need is a few of them. Okay, and that creates a nice big set of residuals. And then there's an issue about how many degrees of freedom. The standard thing about jackknifing is you have the degrees of freedom, essentially, if you're doing a mean, the number of observations minus 1. Because, right? Here, we're dropping columns out. So the right thing would be the number of columns or the rank of the column, typically the column rank of the P matrix that was on the previous page. But then there's an issue of that may be an overestimate because the data don't support that many different profiles. So we use something originally developed by Ron Henry called NumFact, and then Ron and a former student, Park, and myself published a few papers. And we use the minimum of the rank of P, the number of columns, and whatever this algorithm NumFact does, and I'll tell you a little bit about NumFact. It estimates essentially signal-to-noise ratio from multivariate data, and it does it in this way. Ron can give you the papers, and that's the sort of basic algorithm. It's a signal-to-noise ratio based on the ratio of essentially eigenvalues and eigenvectors weighted. I didn't want to go here, but here's an example from some of our papers. This is air pollution. The putative number of factors. This was Clinton Drive. Was 7. The number of columns that we used was 13. Number of observations close to 3,000. Whoops.
Yeah, it's highly multicollinear data. You really don't know what the real rank of the matrices, and you can't tell with the noise. You can't tell just by doing a single data decomposition.
So, and since I've already destroyed this, maybe it works. I probably put the batteries in wrong. Over here. Ron had some spatial data, I believe, from around my area of Texas. This was the Big Bend, sort of Big Bend area. Infrared spectra, train timing data set, word count, where we took works from 5 authors. We knew it was 5 authors, took the 26 most common words and just counted how often they can. And a famous chemometric data set, chemometric melter. And then we tried different ways to estimate the number of sources. Again, we're trying to get the rank of this matrix P. And you can see that NumFact matched it here, got it right. Spatial air pollution, all these. It missed the word count data. The right answer was 5. NumFact thought it was 4. But among all the popular methods at the time, NumFact came at best. And there's a paper coming out in the mathematics statistics literature sometime in the near future by Mike Sherman, who's a theoretical statistician, and Edna Shepton from Israel, that's going to say that NumFact among the existing procedures is among the very best there is. So
oh, really?
It is. Yeah, that's right. That's forthcoming. And I'm not an author on that.
That was invented like, what, 18 years ago?
Right. Yeah. So that's right. All right. So then we're going to take a usual simulation model, meaning the errors are actually IIDs. So we take one of these receptor models. We sample size 50, 9 chemical species, 3 true sources. Errors are independent, and the errors are made to be from 12 to 33%, which is about coefficient of variation, which is about in the range of what we see in real data. Here is the.
Oh, I love that.
Oh, you do like that? You study it. Okay. And anyway, as you study these, and I'm sure you memorized every number, you can.
Zero is wrong.
Yeah. No, I know. And you can't even see the labels on this, and I don't know how to I can get out of it and recenter it. But the point.
That's from a table of logarithms. Don't tell us that.
Oh, okay. Oh, yeah. Okay. So you have to believe, and it's published in this 2007 Chemometrics Intelligent Lab Systems paper, that both methods cover all the right true values. There's like 18 parameters estimate, and they get them all right. All the intervals are about the same size, with the Gap Bootstrap being slightly larger. Here's an autocorrelated example. Boy, this thing moves fast. At least you can read the columns here. This is the Jackknife standard error, the Bootstrap standard error. And you'll see the Jackknife standard errors are bigger, and the degrees of freedom are fewer. The Jackknife, the Bootstrap confidence intervals use essentially 1.96. I think we actually did them from, it's equivalent to using 1.96. The Jackknife standard error would have used degrees of freedom around 3 based on the simulation. So they're much wider intervals, but there's a payoff. The Jackknife 95% interval actually got 95% of the values right. The Bootstrap interval missed 8 out of 18 cases. So there's a case where when you have dependence, actual serial correlation, the Bootstrap, and it's known. I mean, you ask any statistician what happens when you have serial correlation and use the Bootstrap as if things are independent. They are not at all surprised. They'll tell you it's not going to work, and it didn't work, but this thing did work.
So what happens if you have a relatively small number of observations and serial correlation comes and goes?
You're dead. I mean, there's no, I mean, we'd have to talk about what's small and what's big. But in general, to do this stuff, you need observations. And, it's not for sample size 7 or 10 or something like that.
You need to come up with something else. You need a better model.
Right, yeah.
I just have some idea.
Oh no. Okay. So here. So if you go to my stat department, we can get you with the Bayesians, and even if you have one observation, though, we'll get you an uncertainty. But in that case, I refer you to the second slide of the talk, which was the half-life for the neutron. And what you're going to have is a half-life with the neutron with a blessing saying it's certified by a statistician. All right, so this is real data. This is Clinton Drive, and Ron Henry was first author on a PNAS paper in 1997, way back then. And you can get the reference from Ron. It's that.
I still have to wear disguise when I go through airports in Texas.
Right. Yeah, there's a story. We published this paper that said self-reported emissions inventories weren't accurate. And we're writing this paper. This is a story. This is true. Ron goes, you know, you're going to release a firestorm if we publish this, Cliff. What's a firestorm? Yeah, let's publish it. We're doing science. So aside from the press, the head of the Texas Air Pollution Commission, which collects these self-reported inventories and put his hand on his heart every day and said they're accurate, calls up the president of USC and the president of Texas A&M saying, why are you guys blaspheming us? Yeah, that's actually a true story. Except for the putting the hand on the heart. I think he put it someplace else. All right, and so here, you know, and here's a comparison of the intervals, and you can see they're wider. You get wider intervals if you use
With the jackknife.
Jackknife, yeah, with the column Jackknife. All right, so here we go to the Gap Bootstrap. The idea is to break the data into groups where the ordinary Bootstrap can be applied. So you actually have to know something about the construction. This isn't the data set where you know nothing. So you can say if air pollution's further apart in time than such and such, then they should be independent. If traffic patterns are more than so many minutes, hours, days apart, they should be independent. Not the mean signal. I mean, the mean signal can repeat, but the errors should be independent. For example, if people are driving on the highway 5 minutes apart, you'd expect if somebody's late, they'll speed up, so that data is not going to be independent. But if they were late one morning, hopefully they won't worry about being late the next morning, or if some mornings apart. You can figure out, you know, what would be reasonable blocks of data.
So what's the difference between that and the block bootstrap?
The block bootstrap takes contiguous. So there is a board over here. So let me draw this. Typical traffic patterns, and I think it comes up on the slides, would look something like the rush hour one day, you know, rush hour, morning rush hour, afternoon rush hour, morning rush hour, afternoon rush hour. For the block bootstrap, these would be your blocks.
Right.
And so this would be one block, this would be a second block, a third block, etc. And then when you resample, you take a whole block or nothing from the block. The whole block and nothing but the block. If you're doing gap bootstrap, you might form a gap, a non-contiguous block. I need another one of these deals. Here, and you collect the data here, and you would put these together in sort of a block. They're not contiguous. They're supposed to be independent. What happened here is independent of here. They may have the same mean.
Small intervals, though.
Pardon me?
But they're relatively small intervals.
No, they can be big, whatever it takes to get them independent. The idea is you want to break this thing into pieces where this is independent of this, and this is independent of this, and this, and however you want to do it. And the trick is, here's the analogy. You have this function that does this. All right. And if you wanted to fit this with piecewise linear things, you might break it here, 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 and here, and you fit the piecewise things, and this thing isn't totally linear, but a piecewise linear thing fits it well. All right, so what I want to do is I want to use the analogy. I want to break this into pieces, like little pieces, but they're not going to be contiguous, where the independence assumption holds at least for each piece, and the pieces are not going to, you know, I'm going to bag these things sort of in the same group, and then I'm going to take an observation here with here and whatever, and I'm going to bag it.
Oh, I see what you're saying. I see.
Okay, and they don't have to be at the same mean value. They just have to be independent. I want them independent. So what we're going to do is take this data in independent pieces, apply the ordinary bootstrap to the independent pieces. Right? That works. So we could say if we have 100 days data, 23 hours, 24 hours for 100 days. I can take the 8 a.m. measurements from every day and put it together, and the bootstrap works. All right, and then I'll take the 2 a.m. observations, and the bootstrap works. So what I get, sort of jumping ahead, but I do like whiteboards better than the PowerPoints. I get a bunch of theta hat 1s, theta hat 2, and for each of these I can get a standard error 1, standard error 2 correctly by using the bootstrap. The independence assumption is not a bad assumption. Let's hold that. Then the issue is, I don't want 24 estimates, or you don't want 24 estimate. We want one estimate. We want theta hat. And what you can show mathematically is if you let theta hat sort of twiddle equal the average of these things, and you can do a weighted average according to the 1 over the squared deals there, that this is asymptotic. If the original estimate was asymptotically efficient, or if you had n groups, I don't know, n's probably not the right letter, let's say t, and over t, then this is asymptotically as good as the original estimate that you got using all of them, if the original estimate was efficient. And this thing is not hard to get the standard error for totally, because the variance of this is the sum of the variances plus the sum of the covariances. If these things, so there's one additional assumption that says that if you break it into groups, they have to be exchangeable, meaning, and all you need is exchangeable, is the covariance between theta 1 and theta 2 hat is the same as the covariance between theta 1 and theta 3 hat. It's the same thing as covariance between theta 2 and theta 3. Then you're done. And you'll see an example. So the trick, here's the trick. I mean, it's nothing more than this. It really is nothing. I mean, the idea is it's this, not applied to means, but applied to variances.
And they don't have the bias problem?
No bias problem. No bias problem. That's right. Because the model is assumed to hold on the pieces. These pieces are independent, so you get no bias here because they're independent. No bias here from the independent. The sort of where is the sleight of hands? Where's the magic going on? The magic is going on in assuming these covariances are all. That's the Pauler game. Okay. All right. So this slide gives you just what I had put up on the board. We take the theta hats come as solutions to estimating equations, which are normal equations if you're doing least squares or whatever. And almost every estimate can be defined that way. If it's unmixed, you just do it in pieces. It works. We want the estimating equations to show that things are efficient when you put it back together. And here's the estimate of the variance. What I said, the sum of the variances plus the sum of the covariances. And if you assume things are exchangeable, this is a nice little estimate of that piece. It works really peachy keen. So here's a network that we simulated based on real data. It's a Houston example. So we used real data to do our simulation behind. And here's the real data. Here's what the behavior looks like. This is your diurnal pattern, or whatever you want to call it, your traffic pattern. Here's the math model. It didn't get wiped out on this slide. It didn't. I don't know why it got wiped out on the previous slide. And here's the bottom line estimates for the origins. It's the ratio of the standard bootstrap over the gap bootstrap. So if you're less than 1, the number's less than 1, then the gap bootstrap gave a bigger answer. You can see for the real data, using parameters that we estimate from the real data, the gap bootstrap, except for one place, the starting destination, all the others had uncertainties, 5 times bigger than the ordinary bootstrap would give you.
Bootstrap or block bootstrap?
Bootstrap, ordinary bootstrap. Okay, why not block bootstrap? Nobody has worked out for these complicated estimates what the bias correction is for the block bootstrap. You could do it, but there's supposed to be a bias correction. And I'm working with Shuman Lahiri, who's one of the inventors, he and Peter Hall, and he can't do it. I mean, I'm not saying he can't do it. he's not dedicated enough to this particular problem to do it. I mean, he's a smart guy. And you know, this is non-trivial. So he has, so I gave you my version. We started working on this. I said, well, I'm going to do the simplest possible one, which is what I gave you. And Schumann has a much more complicated one. He says it's not more complicated. It's way more complicated. He doesn't assume that the standard errors are identical. I don't take advantage of that, but sort of underlying what I did, the mathematics, I assume these things were identical. He can have slightly different covariance structure between the pieces. And has a fancier estimate, but so there is a paper by the same authors, probably almost exactly reversed, with Justice being a student in the transportation literature, and we're preparing something for technometrics using this sort of method. But it's real simple. I mean, you know, you can go back to the previous. Whoops. You can go back to, whoops.
So you have to make sure your groups of gaps have to be mutually exclusive and cover the data.
That's right, and that's the thing. You got to break it into mutual. So what we do is we assume 1 a.m. Mondays. We put all our 1 a.m.s on different days together, 2 a.m.s together,
Right.
3. And for traffic, there's not much of an argument. Nobody thinks the errors, the deviation from this pattern from one day to the next are really very correlated.
How about seasonality?
That's something we do. Yeah, that's something we haven't tried in our application. So that would be, we'd either have to stick it in the model or worry about it.
Mm-hmm.
But you know, that would defeat us. But
you did it in one season.
If we did it in one season, and the idea is there's always got to be something left for another paper. So I think that's it. So I finished on. I did.
Thanks, Cliff.
Thank you. Autographs will be signed later. So, questions? Oh, that's a pleasure. Thank you.